Hi everyone, so here's another review, but this one's for exam 2, so I'll be going through an old exam 2. Okay, so first question, state whether the following sets are bounded or unbounded. No proof needed. Okay, so how would I figure out if this was bounded or unbounded? Well, for n equals 1, what would we have? We would have 1, whoops, writing with highlighter. So we would have 1 plus -1 times 2 minus 1, that would be 1. So that would be 0, okay. So that's for n equals 1. Oh, okay, but if you notice, so this plus 1, that just kind of always just stays the same, right? So we're just always adding 1 to everything. Now this part is where stuff gets interesting. So this piece here, this gets huge, but then this thing just keeps alternating between negative, positive, negative, positive, negative, positive, negative, positive, forever and always. Okay, so, well, this is going to be unbounded then. Because even if it's a very big negative number, remember our definition takes absolute value. Okay, so how about this one? Well, that could be a little bit easier to look at, would be n over n plus m over n. Okay, so that's just 1 plus m over n. Okay, well, I get to choose n and m from the naturals. Well, if n equals 1, then we would just have 1 plus m, and we know that that's unbounded for m in the naturals. Okay, so this is also unbounded. Cool. All right, for each natural number, let that be that. Compute the sets. Okay, so unioning them, let's first think about what does A1 look like. Okay, so -1 plus 1, that would be 0. And then 4 plus 1, that would be 5. Okay, A2, what does that look like? Well, that would be -1 plus 1/2 to 4 plus 1/2. Okay, so if we're unioning these two together, what do we get? Well, we get this one for the left-hand side, so -1 plus 1/2, which is -1/2. And then for the right-hand side, we get this one, because remember, we're unioning. Okay. Okay, so that pattern is just going to continue because this one's going to keep getting closer and closer to 4. And then this one's just going to keep getting closer and closer to -1 because 1 over n is going to 0 as n gets bigger and bigger and bigger. So let's see. So we're going to have -1, 5. All right, so now we need to pick what our parentheses are going to be. Well, none of them have 5 in them, so we'll have that. Do any of them have -1 in them? Well, no, none of them do. So even though it's a hard bracket all the way up to it, we never actually have a -1 in any of our sets. Okay? All right, so now the intersection. So let's first look at the first iteration. So A1 intersects with A2. Well, now it's going to be the reverse, right? So on the left-hand side, it's going to be the 0 from A1. And on the right-hand side, it's going to be the 4 plus 1/2. Okay, so now the 0 is going to stay the same forever and always because our left-hand side is just going to keep moving more and more to the left. But our right-hand side is also moving more and more to the left. So it's getting closer and closer to 4. So now we have 0, 4. All right, so 0 is the bracket because 0 is going to be in every single set. How about 4? Is 4 in every single set? Well, yes, it is. Even though we have a soft bracket here, it never actually touches 4, so 4 is always in every set. Okay, so how about this one? Ooh, interesting. Okay, so what do we have? We would have, oh, okay, so maybe what I would do is I would call it the even integers as the union. Because if we think about it, so if we think about B1 union B2, what do we get? Well, we would have -4, -2, they both have 0, and then 2, and then 4. So if we continue this, we just get all the even integers. It was very nice. They gave you a very leading line. So the intersection, what do they all have in common? Well, they only have 0 in common. So each of these sets has 0. Okay. Moving on. Give an example of the following. You do not need to provide any proof for the following. A bounded sequence of real numbers that is not convergent. Ooh, interesting. Okay. So let's see. So if I'm thinking about not convergent, one of the things I think about is I think about like sine or cosine. So sine of x, for example, is not convergent because forever and always it just goes like this. Okay. So sine of x on its own. You can multiply sine of x by things that makes it. Okay. And they has to be bounded. Okay, well, great. So if we do, let's say sine of x such that x is in the naturals, well, then each of these is going to be bounded, right? Because if you're just pulling from the natural numbers, sine of x is always, at least the absolute value of sine of x is always less than or equal to 1. All right, cool. So a convergent sequence where an plus 1 is bigger than an. Ah, I see. Okay, so it does have to converge to something. So something I really like thinking about that's convergent is, say, maybe I'll call it Bn or something. So a convergent sequence I like to think about is 1 over n. That's fairly simple for me to understand, but it converges to 0. So Bn is actually bigger than Bn plus 1. So what if I said that a sub n was the negative of this? Okay, so think about this. So 1 over n is bigger than 1 over n plus 1. But if I multiply both sides by -1, I get -1 over n is less than -1 over n plus 1. Because remember, when you multiply it by a negative, you have to flip our sign. Okay? All right, so great. So then that would mean that, I know we didn't have to prove it, but here I am. Okay, so that's what I'm going to choose then. And this was the sequence that I chose here. Okay. All right. So find the following limit. So if you remember, we really pay attention to, so you could take the derivative, the top and the bottom, or you could just pay attention to the biggest power. So the biggest power for both is n cubed. So we get that our limit is 2/3. Okay, on to the next. Using the definition of convergence, prove that the sequence converges to the limit from part A. All right, fabulous. So let's first start by writing out the definition of convergence. So some sequence an converges to L if, and then we'll say for all epsilon greater than 0, there exists some capital N in the naturals, such that for all natural numbers little n bigger than or equal to capital N, we have, I never give myself enough room for this definition. We have absolute value of an minus L is less than epsilon. Fantastic, okay. All right, so now let's start our proof. So if you remember how we do these proofs, first we start by just choosing some epsilon. Choose epsilon bigger than 0. But we're thinking epsilon is very tiny. Okay, well, let L equal 2/3. And now I'm going to hop over to Scratch. All right, so what do I want to happen? I want a sub n minus 2/3 to be less than epsilon. Okay, but what does my a sub n even look like? Oh, wow, it looks like this crazy thing. Okay, so we have 2n cubed over 3n cubed plus 5n. I want that minus 2/3 to be less than epsilon. Whew, boy, that's crazy, isn't it? All right, well, so let's get a common denominator between these two, and then we can really start making some magic happen. Okay, so times 3. So I want 3 times 3n cubed plus 5n minus 2 times 3. So 6n cubed minus 10n. Okay, and I can rewrite this as 6n cubed. Okay, all right, so far so good. So these two cancel. That's really nice. That really helps a lot. And then we have a negative inside of an absolute value, so I could just make that positive after I cancel those two, of course. But so let's see. So what do we end up getting? We have 10n over 9n cubed plus 15n. Okay, well, we could get rid of an n out of everyone. So what do we get? We would get 10 over 9n squared plus 15 less than epsilon. Okay, okay, so it's true we can lose these absolute value signs, but in fact, we can make this bigger by getting rid of that. Okay, and so it's true if, so like, okay, so here's something you need to think about. So yes, if you make this thing bigger, you're not guaranteed it's still smaller than this, but we're in La La Land, so we get to just make up kind of whatever we want. We just need epsilon to be bigger than something, right? So we get rid of this. So now we have, and so now we want to force epsilon to be less than that. Okay, so maybe this is how I should write it. Maybe I should just put these equal. Okay. So I want that to be less than epsilon. So now, if I multiply both sides by n squared, divide by epsilon, I get 10 over 9 epsilon is less than n squared. Well, this is certainly positive. Okay, so there's no doubt about that. So now I just want to pick some n, some capital N, such that n is bigger than that. Okay? And I don't need to worry about plus or minus because I only want my n to be a natural number. Okay, now that scratch is done, I get to go over here and I say, since square root of 10 over 9 epsilon is a real number, then by AP, choose some capital N in the naturals such that bigger than square root of 10. Okay? All right, cool. Then, all right. Then for all little natural numbers that are bigger than or equal to capital N. So, all right, a sub n minus L. What does that equal? Well, that's 2n cubed over 3n cubed plus 5n, which is equal to 10n over 9n cubed plus 15n, okay, which is less than 10 over 9n squared. So this is by scratch. Well, this is less than or equal to 10 over 9 capital N squared, because n is less than, capital N is less than or equal to little n. Okay? And this is less than epsilon, also by scratch. Therefore, by definition, an converges. So why I'm not rewriting the definition is because I already wrote it on this page, so that's fine. Okay, next one. Prove that if n is an integer, then n squared plus n is not equal to 1 mod 3. Okay, so remember, we look at what our important number is, and we're going to use the division lemma. So let's just start by division lemma. And it's always good to write out what the division lemma actually is, or at least write kind of the stuff that I'm about to do. Since n and 3 are in the integers, then there exists unique k and L, I don't know, in the integers such that, oh, I guess we usually use R, but that's okay. N equals 3k plus L. And remember, there's one last contingency on L, so 0 is less than or equal to L. is less than the absolute value of 3, which is just 3. Okay. So L could equal 0, 1, or 2. All right, cool. So what we want to show is that for n squared plus n, it can never equal 1. All right, so let's actually consider n squared plus n. What do we get? Well, we get 3k plus L squared plus 3k plus L. 9k squared plus 6kl plus L squared plus 3k plus L. All right, okay. So we can pull a 3 out of this, this, and this. So let's see. So we do 3k squared plus 2kl plus k. Oh, we could have pulled a k out too, but that doesn't really matter. Okay, so now if we're thinking about in mod, so if we all of a sudden switched over to mod, this whole thing would become 0 because it's a multiple of 3. Remember, that's how mod works. Okay, all right, so let's run through our scenarios. So if L equals 0, then n squared plus n is equivalent to 0 mod 3, right? Because this part's 0 and that's 0. Okay. If L equals 1, then n squared plus n is equivalent to 2 mod 3. Okay, well that's okay. We're just trying to show it's not 1 mod 3. All right, last but not least, if L equals 2, then n squared plus n is equivalent to, all right, well, 2 squared, that's 4 plus 1, so that would be 5. So 5 mod 3. Okay, but what is 5 mod 3? If we minus 3 from it, so we would get 2 minus 3 mod 3. But 3 in mod 3 is just 0. So we have 2. Okay. Therefore, since this is all our scenarios, we have proven it. All right, so pretty cool. And if you, okay, prove that this thing is unbounded. All right. Okay, so what does it mean to be unbounded? It's always good to start with our definitions. So, well, let's talk about what bounded means, because if you remember, if you watch my videos, you know that I like to prove unbounded by contradiction. So if E bounded, then there exists some capital M greater than 0, so in the real plus, such that for all x in E, absolute value of x is less than M. Okay. Proof by contradiction. Assume E bounded. So the only reason why I'm skipping the definition of bounded is because I've already written it up here. Okay, so I wouldn't normally just start a proof like this. Okay, so let's see. So then, well, I'm just rewriting it anyways, I guess. Which means for all k, or let's use a different letter because I think students often get confused with this. So for all natural numbers, I don't care what you call it, as long as you don't repeat again, then the absolute value of 3 to the y is less than m. Well, that's kind of ridiculous, isn't it? Because m is fixed, remember? We can't just keep making m bigger and bigger. So we could do log stuff. That sounds gross. But here's the way that I'm going to be thinking about it. So oftentimes I go over into Scratch. So let's go to Scratch. So one way that I could think about it is a way to get bigger than m is you could do 3 to the m, and this is by calculus. Okay, so if I did if I do AP to choose some n bigger than capital M is less than 3 to the m is less than 3 to the n. Boom, roasted, that's going to be an E. So you don't have to do the Scratch work, but you could. Okay, so by AP, so if you remember, I also give you the hint, you can always just use AP on your bound. Oops. Choose n in the naturals, then m is less than 3 to the m, which is less than 3 to the n, okay, which is equal to its absolute value. Since n is in the naturals, so let's see, do we get integers? Nope. Then 3 to the n is in E. Contradiction. We said for all x in E, that absolute value of x was less than n. Boom, roasted. Therefore, E is unbounded. So remember, I always want to talk about why this element is even in my set. Okay, so I could say a whole lot of crazy things, right? I could say, well, 2m is bigger than m. But how is that helpful? It's not helpful because I don't know that 2m is in E. All right. Next, prove that that equals that. Ooh, fun, fun, fun. All right. So I want to do inclusion both directions. Okay. So let's start. First, let's start by saying that this is an. Okay. And then this whole thing is a, maybe. Okay. So first, I don't know. Let's do it this way. Who's to say? Okay, let x be an element in A. Then, so I always want to think, what does that mean? Then x is in an for some n. Okay, it doesn't have to be in all of them because it's a union. Okay, so x is in an for some n. All right, so what does that mean? Well, then x is in 0 to n plus 1. Well, now you can use my trick of switching that to this. All right, cool. So now I want to show that it's in here. Well, n plus 1 is certainly less than infinity. So we get this is an element in 0 to infinity. Cool. Okay, so one direction done. We still have to do our other direction. So A is a subset of 0 to infinity. Okay, so let x be an element in 0 to infinity. So now we're going to use our trick. Oh, actually, we could say then x is in the reals. Ooh, what can we do when we have an element in the reals? We can use AP. Then, by AP, there exists a capital N in the naturals such that capital N is bigger than x. Consider a, oops. Oh my gosh, I keep doing it. A subcapital N. Well, that's going to be this. Okay. Since x is in here, then x is bigger than 0. So 0 is less than x is less than capital N, which is less than capital N plus 1. Woohoo! Okay, well, we can always say less than or equal to, right? Because it's an OR statement, so just one of the things needs to be true. So, of course, n plus 1 is always bigger than n, but that means it's still true that n plus 1 is bigger than or equal to n. Okay, cool. So then that means that x is in this set, which is equal to a capital N, which is a subset of, so 0 to infinity is a subset. Therefore, since this is how I shorthand my stuff, then 0 to infinity is equal to a. Yay! Okay, remember, I'm not just referring to a willy-nilly, I labeled it above, okay? Congratulations, we're done. Well, not actually, because I'm going to go over some of the problems from exam 1 that we couldn't talk about then because we hadn't gone over that information yet. So let's go here. So give an example of a function that is injective but not surjective. Okay. So injective, that means that none of them are going to repeat. So this is something fun. You don't have to actually define something. You could like as like a formula. You could just do this. So you could send 0 to 5 and 1 to 6 and 2 to 7 and 3 to 3, I don't know, and 4 to 4, sure. Well, this is injective and it's not surjective because it never hits 2. Okay, you could have also said, say g of x equals x plus 2. Okay, then 0 would have went to 2, 1 would have went to 3, 2 would have went to 4, 3 to 5, 4 to 6, and then 7 would have been left alone. So either one is fine. All right, so let h of r to r be that. Assume without proof that this is a bijective function. Great. Write down the assignment rule, domain and codomain of H inverse. So I remember when I gave this exam, a lot of students forgot to write this part, and this is like the gimme points, you know? Okay, so there's the domain, codomain. Maybe you could even label them, although I'm sure it's fine if you don't. Well, what's our assignment rule going to be? Okay, well, I want h of H inverse of y to equal y, and I want H inverse of H of x to equal x. Okay, so let's see, what does this end up being? So this is, so that's what I want, but I don't necessarily have that yet, right? So H inverse, well, where does h take x? Well, it takes it to x cubed plus 1. Okay, so what do I have to do to this to make it x? Well, I probably have to minus 1 and then cube root it, okay? So let's try it. So h inverse of, let's say y, I guess. Let's say that we took the cube root of y minus 1, because it matters what order we do that in, doesn't it? Okay, so I'm going to cube root this x cubed plus 1 minus 1. Awesome. That's just what I want. You could check it the other way as well. That's fine. Or you could just do it in your head. That's fine as well. Okay, so here's our stuff. All right, I think there was one other problem. Yeah, this one. All right, so this crazy stuff. Remember that a generic polynomial can be written like that. Okay, prove that t is an injective function. So how do you prove that it's injective? Well, the way that I like to think about it is, if I injected 2 different elements in here, I would get 2 different outputs. Okay, that's how I remember injective. Okay, so let's start by assuming t of f1 equals t of f2. Okay, well, what does that mean? That means that 0 to x of f1 of s ds equals 0 to x of f2 of s, okay? So I'm assuming that this is true. All right, well, this looks kind of ugly, doesn't it? Well, what do we know about these f1 and f2? So f1, f2 both need to be polynomials of maximum degree 2. Okay, so why don't we let f1 equal, let's say, a x squared plus bx plus c. And f2 can be alpha x squared plus beta x plus gamma. Okay, then we have 0 to x of ax squared plus bx plus c these should be s's. ds equals 0 to x alpha s squared plus beta s plus gamma. All right, so we can actually take the integral of these, can't we? So what do we get? So we get a over 3 s cubed plus b over 2 s squared plus cs, okay, 0 to x. Oh, okay, well, we could literally work that out. So let's work it out on this side. So we get x cubed. Okay. All right, so maybe as you've caught on by now, we can just say that a has to equal alpha, right? Because so if I plugged in the x's here, so the only way would be for a thirds x cubed would have to equal alpha over 3 x cubed. B over 2 x squared would have to equal, oops, sorry, My brain malfunctioned a little bit there. There we go. Equals beta over 2 x squared, and cx has to equal gamma x. Okay? So what does that all mean, though? That means that a has to equal alpha, beta has to equal b, and c has to equal gamma. So f1 equals f2. Therefore, t injected. Woohoo! Awesome. All right, what's part B? Prove that t is not a surjective function. Okay, so I need to find someone in P3 that helps, that doesn't get hit. Okay, so something that can really help you with this is by looking at the work we've already done. So look, so who is not represented by this? Well, we certainly have things of power 3 that we could choose. Just a has to be not 0. Okay, well, wait a second. I don't see any constants. Okay. So how could constants pop up? Well, there is no way, is there? Even if this whole thing was 0. How would we do that? Because we have a definite integral. Oh, my rabbit's sneezing. She's feeling a little under the weather. I don't think she likes this climate change. Okay. All right, choose 2 equals p of x. Okay. If there exists, oops, sorry, I should say proof. If there exists some, let's say q of x in P2 such that, maybe say by way of contradiction, assume there exists a q such that t of q equals p of x. Cool, okay. Meaning t of q, okay, so that's kind of what that means. I know some people get confused about these brackets and stuff, but you really do need them, because t of q is a function. So q of x, let's say that equals ax squared plus bx plus c. Well, we already know what t of qx looks like then. It's going to look like a over 3 x cubed plus b halves x squared plus cx, which cannot equal 2, contradiction. Therefore, t not surjective.